Could we sit down? Probably start on time. Everybody has a seat? Okay, so welcome to the continuation of the stories session. So we have 4 speakers right now. One is talking about new demands for tapes, 2 talking about tapes, 1 actually a new development since the last decades, with very promising, and of course 1 with the update on CERN storage evolution. So first one is Alexei from BNL talking about the Atlas Data Carousel project. And please keep in mind that the second most important criteria is to keep the audience awake. Okay, thank you. Let's start.
Okay, good afternoon. So I will explain what is data carousel and why it is not tape carousel. And what we did so far and what we are going to do and what are our results and why we need all of you to participate in it. It's not about tier 1s, it is about all sides. And I will present some results which we achieved. Just to remind you that Atlas, as any other experiments, we have 4 major distributed software tools. It is production system, PROCSYS, which are responsible for our workflows. It is Panda, which is responsible for our workload. Russia, it is our data management. And Creek, maiden name, Adges, it is information system where we keep all information about sites, about our queues, and so on and so forth. This relatively busy slide, but main message here is the following, that our workflow and workload management, PROCSYS and Panda, and as everything in high energy physics, all of these are abbreviations, but I don't bother you with this. Okay, so PROCSYS and Panda. So all Atlas workflows, Monte Carlo production, physics group production, physics analysis, and recently high-level trigger and tier 0 spillover, all of them are managed by this system. And all our resources, which all grid flavors with what we started at the beginning, and now, nowadays it is supercomputers and cloud computing, are also managed by these systems. And we have quite sophisticated group of shares, priorities, how we share resources between workflows and between users, because requests can be submitted by the whole collaboration. It is called an Atlas language campaign, or it can be physics group, or it can be individual users. And another message that we are scalable. The system is scalable, both. So we are processing more than 1.4 exabyte per year, starting from 2014. And we are certain. So we are, with our workflow and workload management, we are ready for high-LUMI LHC. Another system is data management. It is Russia. And again, so these were years of running, and this data volume managed by Russia. So we are more than 465 petabytes of data managed by Russia right now. And you can clearly see that it is correlated with LHC run 2 with growth. So again, message here, we are quite comfortable. We are certain that with Russia, as well as Panda and PROCSYS, we are ready for high-LUMI LHC. There is no scalability issue here. What we are not so certain is about these 2 plots. So if we will continue with computing model we have now, it is with squares. It will be beyond this plot. And it is true for CPUs, and it is true for disk storage. And for CPUs, we believe we have solution. And LHC experiments were very successful by integrating supercomputers with grid. And you heard about Mare Nostrum, you heard about PITSDINT, there are supercomputers in US, and so on and so forth. This one part of the story. Another part of the story that experiments, I'm a bit biased because I'm from Atlas. Experiments were making effort to go from full Jean-4 simulation to fast simulation. And this is what you can see here, yeah, that if you go to fast simulation and fast reconstruction, your need of computing resources will decrease. There was a question today about new architectures. Again, so we are not that certain, but we know that our event generators and our Monte Carlo simulation potential candidates for new architectures. It can be ARM, it can be GPUs, but even without that, we can run our machine learning applications on new architectures, and we continue to use x86 on supercomputers. So this situation is not so bad. The situation with disk storage is much more scared because you don't have opportunistic disk storage. So there is no way to find something similar to supercomputers. So that's why experiments, WLCG, Iris HEP, and so on and so forth, started several R&Ds. The whole idea of R&D is that run as many R&Ds as possible. And you hear tomorrow about data lake from Andrei Zarochentsov. Today, Iris will talk about BNL R&D. So there are several R&Ds. It is data lake. It is intelligent data delivery system, and about this I will talk a bit because it is related to our data carousel. It is third-party copy, which was mentioned. It is Google HEP R&D project. How can we use cold storage or hot storage from Google as part of our stack? And I will talk about data carousel. What is data carousel? So in Atlas, the model was defined by Kors Boss, and many of you, and this was, I remember Kors because he was from Nikhef. And when Kors was Atlas computing coordinator, he actually proposed a scenario that we use tapes in Atlas just to archive our data. So, and it served well for 10 years. So, and most probably for run 3, we can run this like this. But for run 4, one of the scenarios, if you consider tape as a cold storage, and you keep everything in quotes on your cold storage, and you have your sliding window, and from your workflow management system, you know what you will need to process in the next days, weeks, month, you can stage from your cold storage to your hot storage only what you need, process it, and then remove, and keep only derived data which are needed for end-user analysis. But this is an idea. But to realize this idea, you really need better and deeper integration between your data management and your workflow and workload management, because data management knows about data. Workflow management knows what you are going to process and what is in your pipeline. And also you have another playing this game, you have FTS, definitely, you have Dcache or EOS or whatever, which also can be more intelligent. When more intelligent, I'm talking about us, how we are using it, experiments, can be more intelligent how we use these front ends. So you can define your families or file families or dataset families, which can be grouped together. And this idea is not new, so Dcache people tried to promote it even at the beginning of LHC. And all this can require some novel features to CTA, to Dcache, to EOS, which can be implemented. But again, it can be done only all together. So for data carousel, we identified that we have 3 phases. On phase 1, we just wanted to understand what performance of the tape system we have now, what performance of our archiving system. And it was done last year, practically. Phase 2, this is what we are doing now. Phase 2 is deeper integration between production system and data management system to make all this communication and establish all these protocols between these systems. And phase 3, to run it at scale and to be ready by run 3. So for Atlas and CMS, it is a unique opportunity because for run 3, you can try the ideas which then you will implement for LHC run 4. And this the some results from the first phase of data carousel. It was organized from Atlas side mostly by my colleague Xin Zhao. And this not to say which site is good or which site is bad. It is really to understand metrics, really to understand what is the limitation, what is the minimum and maximum limitation, how you can retrieve data from tape. And you can see that CERN CTA participated on very, very early stage. So CERN CTA, they conducted their test. And for us, it was important to get these numbers, which we used during phase 2. But as I said, so if you will talk with sites will explain to you that if you will discuss it with us early enough, we can do it on different way. For instance, Triumph, they have very interesting way how they write data to tape. And Atlas really benefit when we are reading this data because it is grouped by Triumph using their algorithm. OK, so what lessons we learned during this phase 1? So tape front end is potential bottleneck. And it is, you can have limiting number of incoming staging requests. You have limiting number of how requests passed between backend and disks, how many files you retrieve from tape, and how many files you transfer from your intermediate buffer to final destination. And in Atlas model, final destination can be any tier, because we relaxed with hierarchy model, which we all experience had at the beginning when you have tier 1s and tier 2s and you send data following this hierarchy. So now, depending from your workflow, you can organize dynamically group of sites. It can be more than one tier 1 in this group even, to work together just to finish this workflow. And another important message is data organization. So in Atlas, actually, our unit of replication and processing is dataset. And dataset is collection of files which are processed or produced under the same conditions. And these datasets can be huge. It can be 10,000 files in the datasets. It can be petabyte. Yeah. So, and it's not optimal. It's not optimal as a unit. And we understand this. And it's not optimal to ask sites to place the whole data set on one tape, because then you have penalty when you are writing. OK, so we went to phase 2. And actually, the most important part of phase 2 on this diagram is this intermediate one, when we need to understand what resources you have. Because, and it's not about the disk only, how many files you need to stage. It's also about networking, because you need to transfer this data to other sites to process. It is also about your shares, because, for instance, if you are talking about derivation production, of producing analysis object for a physicist, probably the quota is already exceeded, and there is no much sense to stage this data from tape, because you don't have facilities to process them. And also, production system, workflow management, should know from data management that it's probably saturation or on level of TS, or on level of Russia, or on level of network, and when you don't need to stage data. So, OK, so it was 2 rounds on this phase 2, and I will talk mostly about what we did in August. It was called round 2, when we followed very naive scenario. We have this metrics from phase 1, and we know absolute maximum for each site, how quickly we can stage data. And we tried to stage data in bulks. So we submitted bulk request, and you can see it here. So it is staging throughput at all tier 1s. So all here means all but not Russian tier 1. So it is all tier 1s and so on. So we submit this bulk request, and you see that it was processed quite quickly. And fortunately for us, it was this exercise was collocated with a real data reprocessing campaign of data which we took in last year. Okay, so we so some metrics was the following. It was about 240 data sets, about 7 petabytes of data, more than 3 million files, and roughly 6.5 billion events. OK, so we sent this staging request in bulk. You can see how FTS received them. It was 3 million staging requests, which was received by FTS in 4 hours. And then what we found that about 10% of requests time out finally. Okay? So as I said, it was very naive. So we need to understand this. We need to talk with sites. And I will describe a bit later what scenario we can go. But overall, it was OK. Another issue which we found that the front end, OK, so in this case, it was decache on several sites. And it does not matter which site. It happened in several sites. But you have very effective staging, and then you have crash. And when it is recovered, and you have staging again, and then you have crash again. So we blame only ourselves. So it is the way how we submit it and how we ask data to be staged in. But you see that we cannot really follow this simple scenario. So we need to be a bit more intelligent. And we, as Atlas, we are planning a one-day meeting in December with people from FTS, people from Decache, people from sites, just to discuss, just to identify. And scenario can be different for different sites. The third is tail effect. You see that very quickly you have 90% of all data. And then you have long tail to get in the last 10%. And you understand that for reprocessing, you need all data. And this tail effect explained by these issues which we found when we do this bulk staging with FTS, but also it is for one site. Again, doesn't matter which one. So it is up to 200 attempts to transfer files from buffer to somewhere. Okay? And you can see this profile. So what we think now that maybe we should discuss with all sides, and we can identify a scenario when you will have bulk staging, when you have delay, when you wait until certain level. For example, your watermark can be 50%, can be 20%. It's up to sites to define. And then you continue staging, reach watermark, continue staging, and so on. So this probably will allow us to avoid this and to avoid these crashes with FTS. But this is something to be discussed. I told you that a unit of our replication and processing is dataset. So one of R&D projects which is running by our colleagues from Iris HEP is called IDDS, Intelligent Data Delivery Service. So the idea of IDDS that you can go from this dataset granularity to file granularity. You don't need to stage the whole dataset. You go file by file. And if in this diagram your storage A is tape and storage B is disk, then IDDS take care about the staging files, and you start your data processing as soon as the first file arrived. Okay? So this very interesting idea, if it will work, we want to try it in February, March next year. So again, so it can solve many problems for us. First, it can solve problem that you can wait when certain amount of data is available on disk, and then it will solve a problem that you need to take this information from Russia, and Russia takes this information from FTS. So then you have one service which will work on this. Another important point is smart writing. It is a simulation which was done by Luke Goossens, and it's more or less obvious that if you have bigger files, you have better performance. And what Luke simulated is the following. It is percentage of tape which you read, and it is your read efficiency. And you can see that certainly if you go to 10 gigabyte files, then you really can get better performance, which is probably obvious. But when for a question to Atlas and to CMS and to others, do we really can go to these big files? Yeah, and is it will we have penalties in other places? But again, with smart writing, it is something what experiments cannot solve themselves. So again, so we need to work together with people who are developing storage software and maybe initial grouping of files, and maybe more intelligent grouping when just to use the dataset convention will help. Yeah, because actually when in Atlas language you go to this reprocessing campaign, finally you need all data. And with granularity, which we're supposed to have by February, you can have some data sets, part of them on disk, and then start to process them. Okay, so there are many challenges ahead. So I would say we successfully passed very early stage of this R&D, and we have proof of concept, and we started to work together with sites. Many unknowns problems retired or solved because we didn't understand initially with limitations we have in Russia or in Proti, it is solved. Many known unknowns like smart writing still remain. So this is where we need help from sites and storage developers. What we decided that next year, we'll have two types of exercises. So we can have some technical exercise to check some idea with 2-3 sites. And we'll have global exercise when we'll try to collocate this data carousel with Atlas global data reprocessing. And as I said and try to convince you, it is collaborative R&D. So all these R&Ds which are defined within DOMA, within IRIS-HEP, we need to discuss results together. We need to work together and to benefit from this. So we are planning meeting with all sites in December at CERN. So people are more than welcome to participate with their ideas. And it will be sites, Dcache, EOS, and FTS. And I believe that's it.
Okay, questions to Alexei?
Alexei, if I understood properly, I mean, if you have a site that you are transferring data to, that it has some problems, and then you make a lot of retries, then you might be ending up in mounting tapes like hell, putting files in buffer, the buffers can be deleted, putting the tapes again and again and again and again and again.
Absolutely correct.
And this affects the whole performance of the tape system. So I guess this, I don't know if you have tried to implement in wherever place a mechanism to prevent that. I mean, if you find this type of errors, instead of putting, let's say, more fire into the system, trying to lower down for those transfers until the problems are fixed, or I mean, trying to lower the effect or the impact of this that can have.
Yeah, Jose, you're absolutely right. In our possible solution will be, as far as we have data also at CERN, in this case, you ask CERN as a backup, if you cannot, instead of doing this. And this part of this intelligent scenario which we need to implement. As I said, for a moment we did just straight and naive scenario, but you're absolutely right.
But if you have the problem at the destination, it doesn't matter if you change the source.
Absolutely. But if you have a,
yeah,
but this part which should go to Russia, because if Russia will see that, then Russia should immediately change it. Yeah.
Exactly. Yeah. Yeah, and another things, if I can, it could be really nice for sites to know for the different kind of data that you store at the sites, which are the expected tape I/O that you expect from this type of data. Then it will allow the sites to properly define the tape families, the number of drives they use in parallel to read these tape families, because maybe there is some data that is more important to be read, and some other data that is more important to write and not read. So I mean, this information could be really useful for the sites.
Yeah, correct. And this purpose of this December meeting to also to discuss it, because if you talk with Dcache people will tell you that, okay, we can also try to find solution. But what we want to avoid, that we discuss it separately with FTS, with Dcache, and with sites. So we want all together.
I don't understand quite well which is your success metric. Are you saying that your success metric is how much throughput you can get from the tape to disk, or how much CPU you gain by pre-staging exactly what you need right just before you need it. Like I did not get which is your exact metric, because if you want to optimize for CPU throughput, or you want to optimize for the amount of disk that you don't need, then you end up doing different things, right?
I believe it was on the slide. I didn't say it explicitly. So our metric is to finish campaign in time. And to understand, if you keep all data on tape and you do your reprocessing, or you keep your all data on disk and you do your reprocessing, what will be penalty? So this metric of success, okay? So that if you are keeping data on tape, you will not delay significantly your production to produce physics results, okay? So, and that's why it's not just throughput of your tape system, because you can imagine that you can have more complicated scenario. You can have your archival, you can have your cold storage, and you have your hot storage. And let's imagine your cold storage is something like Google or Amazon, yeah? So then you have even more sophisticated flow between all these three, if I understood your question correctly.
Well, my question was more like, so assume then what you are saying is that what you want to optimize is how hot is the hot disk or the hot storage.
No, we want to optimize that for given budget of our disk storage and CPUs. We would like not to have penalty on physics results. So you need to process your data quick enough with budget of disk budget and CPU budget you have, and networking budget.
Okay, so thanks, Alexei, again. So now we have George from STFC talking about evolution of the STFC tape environment.
Hello. Sorry, yes, is it just right? Okay, sorry, it's okay. Hi, I'm George from RAL. I'm going to talk about the tape service that we're running. So, just short introduction about RAL. This is an aerial view of the site of the whole Harvard campus. So here we run facilities and experiments that are quite expensive to run on their own. And these facilities, the scientific facilities, are provided for scientists from academia and from industries to come and do their experiments. The scientific computing department, you can see there where I am based. This mission is to provide the computational resources that are needed to store and process all the data that are generated by the experiments. So whenever you hear during the talk the term facilities, we mean the facilities that are located in Harwell campus. So mainly what I'm working on is not the processor, not the CPU, it's not the batch farm, it's the storage. So for many years in Tier 1, the storage system that we use for storing data is called Castor, is the CERN Advanced Storage System. So that was used for both disk-only and tape-back data. But during the last 2 years, almost all of our disk-only data have moved to our Ceph cluster called Echo. And what Castor is now used for is for tape-backed data. So we have about 52 petabytes generated by all LHC experiments, and about 60 petabytes keeps growing from the facilities. We do that by running two major Castor instances. One that is called Castor WSG tape, that is for tier 1 data, and the other one is called Castor facilities, which is for storing data generated by Diamond Light Source, CEDA, which is the Center for Environmental and Data Agency, and Jasmine. I said mainly there's not really much disk only. It's not mainly. I said Castor is for mainly tape back data because there's still 550 terabytes from Alice that is stored as disk only data in Castor. But we hope that this will migrate to. They will migrate to use to Echo actually and WSG tape by the end of 2019. So just a bit of description how we set up the Castor WSG tape instance. So it has two sets of identical failure tolerant management nodes that are provisioned by VMware. So there are four stagers, sort of in quotes, because their main mission is to stage the files to disk, but they also are responsible for handling external user requests, whether these are coming via grid FTP or XRD. And we also have two sets of identical name servers. They call name servers because they control the Castor namespace as a POSIX type hierarchy of files and directories, and also controls daemon, and also the daemons that control the tape services are running on these name servers. All these, both of these two sets are served by a single backend Oracle DB. We have a single tape buffer of about 2 petabytes size. We have like OCF 2014 disk servers that are going to be decommissioned very, very soon, and then Dell 2015 and Dell 2018 disk servers. We have a total of 21 tape servers that are controlling an equal number of storage 1000 KD tape drives. And all of these nodes run on SL7 and Castor 217035, so we are happy that this is sort of the closest we can be to the CERN setup. Although CERN, of course, is not running 217035, is running slightly later version. The access to the WSG tape setup is done through DNS round-robin aliases, which are dedicated for each VO. So for Atlas, for example, will be SRM dash Atlas grid pp blah blah, and for CMS will be SRM CMS and so on. This is just a schematic representation of what I just described. The black arrows, not going to go into much detail, they just show the control, the flow of control between the nodes. But I'm going to say a bit about the flow of the data, which is shown with red arrows. So a user is sort of putting via grid FTP or XRD a file into Castor. The stager is processing these requests, is checking with the central name server certain things in the namespace, and then is staging the file into the storage nodes. Once the file is in the storage nodes, it's ready to be migrated to tape, and when enough files are written on disk, then Castor mounts a tape in one of the tape drives that are controlled by the tape service, and then the file is then transmitted to tape. Up to now, we have storage tech SL8500 tape library that is run as a link pair. One part of it is for tier 1 and one for facilities. In total, there are more like 70 drives installed. It's a mix of C and D with their respective media, 5 and 8 terabytes. For facilities, facilities use about 23 C and D drives, but for tier 1 users, we only have D drives, and slightly less, 21. And they handle, as I said, 52 petabytes of tier 1 data. The total amount, again, is this library handles about 110 petabytes. It's obviously still growing and keeps growing. We recently bought the Spectra Definite Tape Library, which is a mix of LTO-8 and IBM Enterprise TS1160 media and the drives in the respective media. Currently, 33 drives are installed, 70 LTO and 16 IBM. The LTO media basically is LTO M7 drive, LTO M7 media. They have 99 terabyte cartridge per cartridge, and the IBM media have about 20 terabytes per cartridge. So in total, 60 petabytes has been installed, and there is another. There's space for an additional 24 without more frames. For Tier 1, so this was basically bought by CEDA, the Center for Environmental Agency, the Environmental Data Agency. So it's for facilities use. But since some money was given by some physics experiments, that is part of the IRIS consortium, we have configured 2 tape servers controlling 4 IBM and 4 LTO drives in WCG tape instance, and they're going to be used by DUNE, the Deep Underground Neutrino Experiment. So this is like, I'm showing again the WCG tape instance after we added the 2 sets of tape drives that are in the Spectra Affinity library. So before, of course, we go into production, we have to test the new library. We have to integrate it with a pre-prod instance of Castor and test it. A simple functional test is basically what? Just write a bunch of files, like 50, via XRD or grid FTP to tape, then remove it from the buffer, recall them, and back to the buffer and verify their checksum. Also did some more sort of, it's not sophisticated, but more close to production functional tests. There are CEDA production tests. So these tests were done using the dedicated client servers that CEDA is using. So these clients are basically, the only basic difference is that they use a different transfer protocol. One client is using RFIO, and the other is using XRD. And here I'm just showing in this table the number of files and the total size that was ingested to the 3 tape pools, LTO, IBM, and Oracle, and then recalled back. We also did some performance testing just to make sure that indeed they perform better than, that perform as expected. So 4 sets of this kind of performance tests were made. Basically, there were large file recalls. So the files were recalled from a single tape in the order. So files were recorded in the order they were stored on tape, and also they recalled in a randomized order. So in the case of a single tape, this was like about 40,000 files. And this is also done, the same 2 types of tests were also done for multiple tapes. This was about 40 to 50,000 files of various sizes. And for every successful transfer to a tape drive, Castor reports drive transfer speed in megabps, which is basically the speed of the transfer to tape. So a possible metric would be an average of these values for every file that was successfully recalled from tape. But because our tape buffer in the pre-prod instance was quite old, well, it has 2012 and 2013 generation disk servers, all the file transfers that they had that stayed too long in the memory of the buffer were discarded, and also were discarded all these file transfers that had a very large position time. So for these transfers that the drives required too long time to position, to find the file. So after we discarded all these values, we averaged the drive transfer speed megabps, and these are the final values here listed for the various tests that were done. So as expected, the IBM drives perform better than the LTO, so we have like about 310 megabytes per second versus 291. Even more, the difference even more is starting in the case of random reads. And again, the same for multiple tape order reads. In case of the multiple tape reads, there's an average bit of this value across different tapes, so that's why there's a standard deviation there. Of course, all this performance testing is fine, but the question is how this will perform in actual production conditions. And this is sort of one case of this scenario is the Atlas tape Carousel in 2010. Actually, as Alexei mentioned, it's not this separate Carousel, it's the round 2, probably, of the Carousel. So this was a large unannounced reprocessing campaign. So from our point of view, what Carousel means is that thousands of files are requested from the tape, and we have to deliver them with the maximum throughput as possible. So from our point, in RAL, about 1 petabyte was recalled between 8th and 19th of August, and 70% of these files went to the RAL Echo, it went to the Ceph, our Ceph storage, which is only for disk. And the rest went to smaller tier 2s, like Glasgow, Manchester, and Queen Mary. In this exercise, only our storage tech drives were used, not the IBM or LTOs. And initially, only 9 tier 1s, not only 9 tier 1s participated. But due to an unscheduled downtime of CNAF, the share of CNAF was reassigned to CERN. And that's it. So here I just show a plot that shows the utilization of drives, not from the very beginning of the Carousel, but in the last week of the Carousel, between 13th and 20th of August. So in a pool of like 20 shared drives, the utilization by Atlas is not very bad, as you can see. And in terms of actual performance, I know you said you didn't want to say which site performed better, but the temptation is too much for me to escape, and I can say that we're happy to say that we performed better than the others. But this is not a criticism by no means, a criticism of the other tier 1s. It's just that it was an encouragement that our setup of this Castor instance, including the tape pools, the grouping of the tapes, the recall groups and everything made some sense. But I am not satisfied even with the current status. So I would like to get even better performance. So this is from a talk given in, as you can see from the Panda, it was given during the Atlas Software and Computing Week in CERN, in the Data Carousel session. So what is the future of Castor? The future of Castor, it has served us for more than 15 years now. It's sadly, at some point it has to go. That will happen before the start of the LHC Run 3. We don't know what exactly we're going to replace it with. We're looking at different options, commercial, non-commercial. We had a very productive meeting with the storage people at CERN, Steve and others, to evaluate the CTA system. And we also want to procure a new tier 1 tape robot, since, as I said, the Oracle will go away. Actually, will drop. We'll stop developing new libraries by 2025. So we really want to move away from Oracle. That's it. Thank you very much.
Okay, questions? You all happy with your tapes? I can't imagine. Can't be true. I had a question.
Yeah.
I mean, you have these performance figures, and you have the magic juice, actually, because you see faster recall times or higher bandwidth for random access on your tapes instead of sequential. that sounds critical. Did you operate these?
Sorry, you
tape
said,
drives
is this
with
for the performance testing? Yes.
Yeah.
Oh, yeah,
Did you access or did you use these recommended access order?
Yes,
feature?
yes. So this was all done. No, sorry.
So if
sorry,
you look at the TS1160, the random read is faster than.
Very good question. No, because this was done in a pre-prod instance that ran a sort of older version of Castor that didn't have the recommended access order implemented. So this was not. Run with RAO.
Okay. And if you have these multiple tape, that means you didn't restrict the test to one drive. That means in this example you use more than a single drive.
Yes.
Okay, not just more tape, but also more drives.
Yeah. That's what I'm saying. Well, a single drive is a single tape, so more, yeah.
Okay. Further questions? That's not the case. Thank you again.
Thanks.
So next is Stephen from CERN talking about the status of tape storage at CERN, which actually means or focused on CTA, I guess.
No, that's the previous one.
Sorry,
Status.
stage. Why is it not here?
So it's cancelled.
No. It was here. Data loss.
There it is, this meeting there. No,
This one?
Open that one up. Yeah. Okay, good afternoon. I'm going to just talk about tape in general at CERN. So there's many authors on here. I'm from the CTA development team, but I'm going to talk about things that are not CTA, the new CERN tape archive. So let's get into it. So this is the usual graph at CERN we always throw up. So I put that there for everybody. So you see, and this year things haven't changed very much with the shutdown. We've had some data written and some data deleted, I think, by CMS. So just to give you a rough idea, in terms of archive data, and that's what goes into Castor, we have 335 petabytes. And on TSM, which I'm not going to talk about in this talk, we have 12 petabytes of backup. I'll move on because the numbers people can read after. So what do we do from an infrastructure point of view this year? We're getting out of Oracle. So we've basically nearly gotten all the way out. So that means we repacked 80 petabytes of data. You'll notice on some of our plots that it's not exactly zero because we've got a few bad files and bad tapes, the crud at the bottom of the barrel. We physically removed two of the Oracle libraries are off the CERN site. And we're trying, if somebody wants to buy 2 more Oracle libraries, please contact Vlado. It's not a joke, it's serious. He really wants to flog this, I don't know, the local market. But so if anybody's interested, seriously contact Vlado. I go into some of them, just so everybody knows, we have a TS 3500. We've upgraded that to a 4500. We've extended a 5,000 slot IBM to the full capacity, 20,000. Don't want to scare anybody here, but we did some successful tests of replacing some of our fiber channel links with the Ethernet. I've been told I have to be careful with this because this required ROCE, so that's remote data memory access over converged Ethernet, which is not a normal Ethernet card. You need special hardware, and this only works for the enterprise drive, so this isn't going to work on LTO. Anyway, it did what it was supposed to do, apparently, but just to say we did that. Okay, this is fun photos, really. On the left, we have some people standing next to Oracle, and on the right, it's been carved up into lots of pieces ready to be sent off site. This big blob of red in the middle, which nearly goes to 0 at the end there. That's Oracle. That's us getting rid of Oracle tapes, the data coming off. And that patch of dirty, creamy, yellowy color in the middle, that's LTO. So one thing we want to get across is that we are going to be using LTO technology at CERN, and I'll come back to that later. So staying with infrastructure just for a moment, what we're going to do in the future, of course, is prepare for run 3. So we're going to increase. What does it mean for us? We think that we're going to be writing over 150 petabytes during a year with peak rates above 40 gigabytes per second. We're not expecting sustained rates above 40 gigabytes per second, maybe 20, but I won't say too much more on that. We are going to increase the number of tape drives from 100 to 160, and then based on availability of all the equipment, we would like to buy LCO9 drives if available in the fourth quarter next year, and TS 1160 drives if they're also available in the fourth quarter. And in the beginning of next year, we will be installing a new LTO tape library. The tender is still going on, so I don't know what we're going to get. We're going to get something nice and shiny that's not IBM. I don't know. So coming on to the bit where I could probably bore you to tears, so I will try to move fast. So CTA is the replacement for Castor. I think everybody knows that by now. It's a bit confusing. So CTA is something that sits on the back of EOS and makes EOS tape enabled. I think that's the easiest way to explain it. We chose EOS because that's the main disk storage we have at CERN. Basically, we're taking the best bits, I should say that, as a tape developer, the best bits of Castor and sticking them on the back of EOS. We will use the same tape format, so we only have to migrate metadata when we move the existing Castor data across to CTA. We're just going to change the ownership of the tapes and make sure CTA knows where all the files are. Okay, internally for us, it means that we don't have to develop Castor disk anymore. We write on the back of the EOS disk developers. Yes, CTA will do things simpler because we've started the project from scratch. So scheduling and that will be done in an intuitive way. We will, talking about databases, at CERN we're trying to get the number of relational databases used down in number because we're using Oracle, and we would like to also get out of Oracle databases as well. So CTA only has one database. We shoot anybody next to the chemical plant if they use PLSQL and start putting business logic in there, because the marketing department of Oracle keeps getting people to use Oracle-only features, and we're really trying to stop this. So at the moment, there's no PLSQL logic. It's very simple SQL commands. And less network components than Castor, but I think that's an internal argument between developers. I think we won't discuss that here. It caused a bit of confusion because when we sell EOS and CTA to the experiments, we would like them to use FTS as well, if this is possible. So Atlas have been really nice because they use FTS. We work really, they've been too good to us, Atlas, to be honest. CMS will also be using FTS, I believe, with Lucio, so we're very happy. However, we have to tailor EOS CTA to fit all the experiments. Not to say that Alice does things differently, but they're the most different on this here. So in the case of Alice, we are going to give them a little bit of HSM-like behavior because they're used to that with Castor, and they can't get rid of all of their dependency on this. So we are going to do some custom tailoring for the Alice experiment, but Atlas very well behaved. It's FTS and us. CMS, we hope, we've been talking to them, we're going to do the same thing as Atlas, so FTS as well. LHCb, we think they will be the same as Atlas and CMS. I think the main problem for them is dropping SRM. So that is just to say this is a complication. I think the main complication for LHCb will be that. I've put this up because time and time again people get confused. So EOS CTA has an incredibly small disk storage on it. It's not a cache like Castor. You cannot retrieve files in it and expect them to be there 3 weeks later. It is simply a very thin SSD buffer that it puts files in at one end and they come out at the other end and they're very short-lived. Now, that's not to say, yes, with Alice, we're going to solve the problem. We're going to give them a big disk area to do their HSM behavior, but this is the model that we prefer. Why are we doing this? We are trying this time to get the most out of the tape hardware. We're really pushing it. So hard disks, they thrash a lot. By the time you get as many spindles as you need to avoid the thrashing, you end up with people wanting to use the space for storage because you get up to several petabytes. So we're going for SSDs, and that's to avoid the thrashing and to get the number of components necessary down so we can manage it. Just again, so there's no confusion, each experiment will have its own dedicated small buffer. So there's no worry about people interfering with other people when they're pushing things through. Everybody, of course, shares the tape drives, and of course, everybody has their own tapes. Right. So I'm moving on to the operational side here. What did we do since the last HEPiX? So we have Julian, our operator, has moved our instances, because we have instances that we are allowing the experiments to use, mostly Atlas. We've got them off the spinners. They're on SSDs. I'll just summarize this all very quickly. We put a very small instance together with 5 machines and 20 terabytes of SSDs, and we allowed Atlas to have access to all their Castor data through the CTA software. And I think we beat everybody on the test for the recall tests of Atlas. Of course, we were cheating because we had all these SSDs and we had some developers just tweaking it all the time. So, it wasn't a fair race. Atlas, of course, were very happy. So here's a plot I don't fully understand. I mean, the bottom line is we could push the hardware only as fast as 3 gigabytes per second, and as you can see, we did it for a moment. So the argument to management would be our software does not get in the way of the hardware. The more I look at that, I don't believe it, but it's, we did it. And here's us winning the race. I was trying to show this, but it was no race. This was during the Atlas recall campaign. We're the blocks in red, and we managed to get everything back first for them, though there's bits of red at the end, which there's a lot of strange explanations as to why that's there, but okay, we cheated and we won. What are we doing for 2020? Well, of course, we've got to get all the 4 LHC experiments across to CTA. We will be ready in November for Atlas, but we don't want to pressurize Atlas. It means from November onwards, they're free to come along and ask us to go into production. I think realistically, we're looking at everybody from the beginning of next year we will start. So probably Atlas will start in January or whenever they want. We're in tough discussions with Alice right now. We've got to change a few things for them. CMS, I'm not worried about. At HCB, yes, we still have to discuss the SRM side of things. Once the experiments are done, that's when we want to tackle public, if we could do that, because public this is the Castor instance for general purpose, and it's got so many use cases. And the people that probably wrote the frameworks that nobody understands anymore are probably dead by now. So trying to deal with this is going to take time. So we'd rather delay that and do the priority of the experiments, the LHC experiments. What did we do this year in terms of development? We finished the repack software. I think everybody knows if you want, you've got to reuse your tapes. You want to put them on higher capacity so you free up your slots. Support for multiple database backends. This is the strive to get away from Oracle. I'll come back to that. And talking with Atlas, We are trying to put in the extra metadata that Atlas want to color their files a bit more and say the purpose of this file was this, or the activity that produced this file was that, so that we can maybe collocate things or do more efficient recall campaigns. So we're trying to get as much of that in as possible. So the database backends. After all that's been said and done, we will run in production with Oracle at the beginning, because from a risk point of view, the Oracle databases we have at CERN are fully covered and everything is fine. We want to get out as soon as possible. So I think at the moment, CERN will eventually move to Postgres as a production. This is what we recommend for the tier 1s. We also have MySQL, thanks to IHEP. They sent Lin Tao to us, and in 2 weeks he put the MySQL backend as well. So this is just proof that we haven't done any tricks with Oracle that cannot be ported to other databases. So this is the bright future that we also want to implement, and I come back to the LTO. LTO does not support recommended access order, but we are going to put in CTA, we would definitely implement a poor man's version of recommended access order. Herman Cancio gave you the paper before. This is still on the planning. We're just not doing it. We haven't done it this year. We hope to do it next year, but we're going to need it, and that's the way to use LTO. The tapes drive scheduler, we're going to make it preemptive next year. This is just so that operators can run repack and not worry if an experiment needs to do something high priority, then it would just push repack out of the way. And it's a background activity. It's not crucial for the running of the laboratory. We're going to give more, we promise to give more tools to the operators, or maybe not, we let them suffer a bit. Of course, we'll catch up with XRoot D5 if it's there. There's some features we might be able to use, like extended attributes. And of course, we'll continue with Atlas with these collocation hints. I think there's more to it than just sending the metadata around and storing it in our DBs. We have to look at that in more detail as it comes along. I believe that's it. I think I've managed to do that quick, because it can get a bit dry. Okay, so.
Okay, questions? Oh.
Yeah, thank you for your interesting presentation. On slide number 9, I think you were saying that the tapes are shared among the experiments.
No, the drives are shared.
Oh, the drives are shared.
Yeah, the drives are shared, yes.
Okay.
Not the tapes.
Sorry, my
Good God.
misunderstanding.
Good God, Atlas and CMS on the same tape and you lose it. No, no,
Yeah.
no, not
Okay,
gonna happen.
Okay, thanks.
Further questions?
About that slide specifically, as the tape drives are shared, what would happen if some cache would be full and maybe all tape drives are full as well?
So, yeah, the scheduler is fair. There is a central scheduler for this, and we are not going to allow Atlas to grab all the drives. All right, there's going to be a fair share.
Okay, so you always keep 1 or 2 drives for another
Absolutely.
experiment if it doesn't use them.
Cool. No,
Yeah.
Absolutely. No, we won't. No.
The fair share in the tape drives, is it per consumed time in the drive, per data amount of size move, or amount of files?
Let me think. It depends on the problem at the time. I mean, if everybody goes on at the same time, we're just going to give them the drive time. So we would divide the drives up. What happens in practice, however, is if something goes crooked and somebody has not had their drive time, operators will come in with dedications and make sure that they catch up. okay? But on a good day, it would just, if everybody's in at the same time, they'll have an equal number of drives each. All right? We're not going to be going and looking at saying, well, they're not using it as efficient as the next guy. I believe at this moment, it'll just be a fair share of the number of drives. Okay.
Okay, last chance. Okay, otherwise, thanks, Stephen, again. Okay, the last talk between you and the coffee break is Giuseppe from CERN talking about, it's a catch-all title, CERN Storage Evolution. So probably he will cover everything regarding storage at CERN.
Yes. And I can use... Okay, so good afternoon, everyone. Yes, so I will give you, this is a talk actually on behalf of the entire group, so it's kind of complementary to what Steve gave on the tape side, so this is more covering the disk side of the storage at CERN. So I will give, the first part is really across all the storage services. I'll try to make it not too long because otherwise it looks the boring part of it, but then I try and go a little bit for a deep dive into some specific topics. First one being related exactly to what Steve presented, so how we are tackling this migration of the tape archive system. Second one comes back to what was discussed the first day also by Thomas and others in our department, so all that is going on in migrating to open source and away from basically licensed software. And then there is also a transition. We'll announce something around a new European project. So starting with the different services, of course I start with EOS. Many things were already mentioned actually even by Andre in his status report. I could stress here the fact that, well, okay, we have at the moment order of a bit over 100 petabytes of data on disk. And the total capacity, it's this number. I mean, this is what is deployed at the moment at CERN, with the caveat that a quite significant part is actually coming over. So part of it is due to the Wigner migration that you heard about, especially from Wayne. So this takes time, of course. We have to dismantle the servers on one side, bring them back, put them back in, then do again the burn-in test, etc. So there is some capacity which is always a bit frozen on the way. Plus there is extra capacity that is coming over. So this is still, there is this figure, we have in the order of 70 petabytes that are supposed to come rather soon. And so this will be coming up to pledge. Otherwise, at the moment, we are actually even below pledge. I mean, that was kind of expected. I mean, you can quickly drain batch, well, kind of quickly drain batch, but draining data and it's more complicated. Coming to Castor, just to show a little bit different picture, this is what happened in Castor in the last 6 months, so basically since last HEPiX, so pretty much nothing because there is no data taking, except this big dip, which is indeed CMS doing a bit of cleanup, but nothing really special. So what is happening on our side, indeed, and this I will mention in a moment, is the migration to CTA. Otherwise, then we have Ceph. Ceph is at CERN deployed into multiple instances. And here you have a summary also of the different versions. So there's also kind of a mix. We have just finished to upgrade the 2 instances. Actually, this one was a kind of test, and by now it has been even decommissioned. So there is no more Ceph at Wigner. And we have only 1 instance at the moment, which is actually used as a tape buffer, as a disk buffer for tape behind Castor. Well, if you want more details, we can talk about that offline. I know part of it, but I'm not the main operator in this area. Actually, one interesting part which will come after is this what we call those hyperconverged clusters, because this helps to do interesting things with, for example, with the mail servers. Now, AFS was also mentioned at the beginning, and I promised a little update. So what are we doing with it? Yes, this phase out is going on for some time. In fact, in a way, the kind of good news is that we see a little bit more movement upstream. So we are a little bit less concerned about that. even though in general, anyway, it's not like things are going to improve very much in the future. So this kind of mixed feeling, so what is the strategy at this point is that AFS is going to keep going for some time. I mean, we're not going to shut it off anytime soon, but we are trying to move as much as possible services out of it. So whenever there is a good alternative, we typically propose to the different users, projects, etc., to use a different solution. And we'll see how to evolve all of this in the coming years. But I clearly see AFS being there in the run 3 without any major issue. And then Sandbox on the other side is a kind of, for part of it, the replacement of AFS, at least for home directories. This is really still growing even after 5 years of service. It's still growing quite a lot. And to give an example, this is 24 hours traffic on the HTTP doors. So basically, during the night, we're just below 200 Hertz, and during the day, we go up to 400 Hertz. So and these are the connections from all the scene clients, right? So the desktop clients that connect, or even from the, most of it is that, and then you have also the interactive, the online users that really use the browser. So this is indeed quite a significant service in terms of usage and traffic. And what's going on now is that the core daemon running behind, which was based on OnCloud, OnCloud is actually the framework on which we are working, has been basically completely rewritten in collaboration with them. And this is actually, there is an interesting collaboration there that is going on for this part. And finally, okay, just a little flash on Swan, which is in a way connected to Sandbox. It has been partly mentioned in some other talk, but just in case people interested in it, we have just had a workshop last Friday, a week ago at CERN. So this is where we basically gather together all people using it, and I mean, mostly from the experiments. And I must say that the variety of use cases that are now running on top of Jupyter notebooks, I mean, that's the core of Swarm. And then this integration with all the different services that are put together, it's quite impressive. So it's really something that is growing almost like the one-stop shop for analysis at CERN. And another interesting part is also that all of this has been containerized. I mean, nowadays, you know, we heard already about containers a lot. And ARNet in Australia, so this is the national network, basically, the National Academic Research Centers. They've deployed this same stack on containers, on their own infrastructure. So in the end, yes, we are binding to everything to the CERN services, but it's working on its own. I mean, it's rather easy to run it pretty much anywhere. Okay, so with this, I gave you a little bit like the landscape where we are moving. So you see that there are services which are really greatly evolving, other ones where, in particular, AFS, we want to try and reduce the usage. Now, to get a bit into let's say, those selected topics. So first part is this castor migration, which I titled just for making fun of it, how to migrate this large archive without really moving a byte. I mean, otherwise, we wouldn't be able to do it, especially not in a decent time frame before the experiments start again taking data. So in fact, yes, it's true that, I mean, as Steve explained, the CTA effectively is the evolution of castor. It's the same data format, so the data is exactly the same. So we just have to migrate the metadata. And even for that, it has been anyway rather complicated, not just for the technology of copying files, I mean, copying the data, or the metadata across databases or across the namespace. So there we have the EOS part runs on the EOS namespace. But actually this part, this kind of analysis that has been carried over has been rather complicated because, of course, this is the archive system that has been used at CERN for, as far as I know, at least 20 years, even before, because this is the evolution of Shift, which was written in the 90s. So there's a lot of legacy there. And it's not obvious to see, to do the right thing according to the experiments. And, okay, these are the figures, again, just for looking at the Atlas recall campaign in August from this point of view. So to help them run the campaign, we did this export, and in fact, it ran, so they have at the moment in the order of 80 million files, and this happened during alpha day, basically. So we managed to give them access to the entire data collected so far through the new software with alpha day of metadata migration. So from this point of view, I mean, the code and the tools, the tooling around this migration is ready, and then, as Steve mentioned, we're going to look after all the different experiments to really do the migration at this point. And only to scare you very quickly, this is how we analyzed the namespace, which by now, of course, is not just a namespace, a hierarchy. We have tags which represent how to do tape families, how to do this, how to do that. And when you want to put everything together, it becomes a kind of a multi-dimensional space where you want to, I mean, you need to look into some details, because the evil is always in the details, of course, and we need to know how to do things properly for the experiments so that they will find back the data correctly. So that's all about the tape migration. Now we're going to MALT, which is the nice acronym I don't want to pronounce, which you know anyway very well. I mean, all of this, you know that the core of this project has been and is being to migrate away from proprietary software wherever possible. So in fact, sorry, here the first part of it was already presented. It's the mail service. And in a way, kind of answering part of the discussions, how much does it cost? We would need to even fold in the cost of the different services that now are being involved once we choose, rightly, I would say, to use the different services and do this kind of Lego bricks one on top of the other. In particular, on the storage side, for example, we had to put in place a CephFS share for the mail attachments. This is how Copano runs. I mean, it's a file system. And this is the hyperconverged part that I was mentioning. The Copano servers run on virtual machines, also on OpenStack, and the same nodes run a self-storage, which is visible by the machines themselves, and all of this on SSDs. So that's the way to get really good performance and minimum latency. So this cluster is on its own doing everything. So both giving the virtual machines and giving the storage based on Ceph. Is it worth it? My take on it is that this is worth simply because we need to be able, at least to show that we are able to detach from proprietary software. So in the long run, it is profitable anyway. Apart the stories about we want to keep the data because of well, you know, the status of the CERN organization. We want to keep it at CERN. So cloud services in this case are basically not an option. Otherwise, probably, I mean, my take would be that we would have moved to Google or whatever else even long ago. But no, we cannot do that. So it is worth moving there, even if it costs across all the different services in the department. Another part of the MALT evolution, this was also mentioned by Vincent. We are migrating people off of the Windows DFS home directories to Sandbox. Now, by definition, this means people that are very much Windows-oriented, and now we tell them use a service which was born on Linux, effectively. I mean, the native access is basically on Linux. It's a fuse mount on Linux. So immediately they ask a Windows gateway, which is based on Samba. So this is something that we've been working on during the last few months, and very recently we put in production an available cluster for those Samba gateways to ensure indeed this, let's say, available, more reliable way to access the storage. And this actually has involved also a couple of analyses that we did. For example, I wonder whether other people had similar experiences. By nature, the CIFS protocol, which is the basis of the Windows network protocol, is very slow when dealing with a lot of metadata. So if you want to delete an enormous amount of files, it can take 10 to 20 times more than deleting from a fuse mount on Linux. And this is just the protocol itself, nothing to do with the backend. It takes 10 to 20 times more just because you go through this protocol and maybe you just access a local disk. Then the extra overhead of going to a remote file system, yes, of course it goes in the way as well, and you have an extra little penalty. But the big part is really the protocol. So this is something that we are trying to look into, but the complexity there is that the protocol is what it is. We can't really change the protocol. And by the way, so this is a little bit the traffic that we have. So we are now consistently having in the order of 300 different clients. Well, okay, this is the weekend. And then again, we go on. So this I took it last week. So it's quite significant. And to give also a little, so this is really going a little bit more deeper in the architecture that could be maybe useful to someone. So the way the Samba software runs a cluster is that they require, I mean, this is requirements from the software itself running the cluster. They require floating IPs. So you cannot use the IP bound to the network interfaces of the boxes. You have to have extra IPs that are dynamically assigned to the machines offering the service. And then the daemon itself is taking care of reassigning the IPs in such a way that if a machine goes out of the cluster, you don't need to wait for the DNS caches to refresh, etc. Immediately, that IP is picked up by another one, and it's always online, effectively. Until there's at least one machine in the cluster, all the floating IPs are always online, which is convenient. Basically, we ignore, we don't have the problems of the refresh, of the DNS refresh caches, etc. On the other side, this is almost like a joke, but the way to share the state, because of the protocol being stateful, is through a shared file system, which is exactly what you are trying to provide. So to provide a shared file system, you need a shared file system. And our choice went to CephFS instead of the same EOS file system for the moment, simply for convenience. I mean, there is no special reason, let's say. One reason is also the fact that if you were to choose a specific EOS instance, that would be kind of more critical than the others, because that one having problem, the entire Samba gateways would have problems. CephFS so far is kind of more targeted for these kind of usages, so we are using it successfully in this sense. To be honest, I don't have any special preference in the sense that if we find CephFS not to be that good, that much reliable, we could even go and run on an NFS share on the same machines, for example. This doesn't need to be the same file system that is then exposed to users. It can be anything, effectively. But still, it's interesting that you still need another pieces there. And then the other part that was also a little bit of a challenge is that because of how the Windows domain, the Active Directory works, you have to play a little bit with the key tabs. And this, I guess, even with the new authentication system, anyway, this holds, because all of those machines talk and behave in the network using those floating IPs, not their original IPs. So they are effectively like a different network identity. So depending on the authentication system, this has to be taken into account. Okay, that's all I want to say on the Samba side. And now I go to the last part of this Malt exercise, let's say, which is more on Sandbox. This is already something that was presented also at HEPiX last time. I mean, it's going on the same route, if you want. That is trying to integrate into the Sandbox web interface more and more applications, even just for office productivity. And you see very well that in this list, there is nothing proprietary. Definitely, there is nothing Microsoft. So this is the recommended replacement for Microsoft Project, this for Microsoft Visio, and those two for all the rest of Office. With this still being tested, this will be the LibreOffice, OpenOffice format, with all possible caveats about the format. Yes, true. That's why most likely we are going to offer the two of them, because there will be users more on the open format and other users more on the Microsoft format, which is more supported by this solution. So this is a trend that is ongoing. We're going to have even more of those applications, and in this case, the other group, CDA, so the collaboration and documents and applications, indeed, the group is mostly involved, with Sandbox being kind of the platform where to run all of those things. And in fact, here the story is actually that the applications is one dimension of the problem. But then you have at least two more dimensions of the problem, being the fact that you have, if you want, the raw storage, so this being EOS or S3 or whatever else, and also many other possible vendors like on cloud that provide this kind of sync and share. So here I put a few of those possibilities. There are many companies that actually provide these kind of solutions based on sync and share. How did we get in touch with all of those people? Actually, thanks to a series of workshops that were advertised already at HEPiX. It's not the first time, even myself, I advertised them a couple of years ago, which is this, what we call the CS3 community, which stands for Cloud Storage Sync and Share. And we are now at the point that together with many others, in particular with OnCloud, because, okay, we are working in very tight collaboration with them, as Sandbox is based on OnCloud, we are defining some kind of vendor-neutral APIs. So this is what we call the CS3 APIs, which basically are, I mean, the dream or the vision, if you want, would be to be able to connect on the same storage different applications that are able to also share with other different storages or other different sync and share solutions. So this could be, that's why it's like really multi-dimensional at this point. Because otherwise, at the moment, if you want, the panorama is rather diverse and heterogeneous. Everybody went for their own solution because the market actually requires that. So all of those, they have their own little share. And I'm not mentioning the big names, of course, but okay, to be seen whether they would even participate, like Google Drive, I don't know, or Dropbox. But you see, so this would be like the trend where to go. And in fact, it's exactly in this context that this new project is going to start. So basically, we went through the standard European call for Horizon 2020 projects. And we just had it approved a couple of months ago. So this is a project that is going to run for 3 years, starting from next year. And the idea would be to actually put together all of those partners, exactly what I just showed, around, and okay, even under the umbrella of the European Open Science Cloud, which is an already existing European project. So it's not like really doing something completely out of the blue and not connected with what exists. The idea would really be to develop the glue to be able to use what already exists and what can be maintained and sustained in the long run. And probably this was why the project was successful. Because otherwise the risk, of course, is to create something. Then when the funding finishes, the entire thing is dropped because it's out of the scope. There's no ecosystem around it. In this case, the ecosystem is the European Open Science Cloud, is the other sites that run similar things like Sandbox based on OnCloud or NextCloud or whatever else. So the advantage in general, thinking really about the HEP community, so all the different sites, would be to have this kind of collaborative environment and sharing, not only within, for example, CERN, so with my CERN colleagues, but being able to share a project, notebooks, analysis, whatever, across sites and across different storage instances. So me at CERN sharing on Sandbox something, and then somebody at INFN will take it as a Garbox share or a Daisybox share or whatever. So this kind of interoperability is actually what we are trying to target, which I believe is actually could be beneficial then for everybody, especially for the large collaborations that we know are now basically the default. No? I mean, Atlas and CMS are just the first ones that are doing this. And with this, so this CS3 community itself is actually a rather active community. I think in this place, I've announced already, this was already announced even by my colleagues, we've been running a workshop every year We are now at the 5th edition. This has happened early this year. So this is actually the forum, if you want, where we meet everybody. And so this is where those ideas and to build up something that is not just meeting together, but really developing something in collaboration in a vendor-neutral way, has actually born. And so I finish with some advertisements. We are going to have, of course, the next workshop. This is going to be early January, well, late January, early 2020. So end of January 2020 in Copenhagen. The abstract submission has just opened. So for people interested, well, either approach me or you go to the website for more information. And with that, I conclude. Thank you.
Okay, we are at least 10 minutes ahead. Questions to Giuseppe?
I'm really curious about that initiative of CS3 API. Is there something existing, some kind of first RFC or I don't know, things like that, or it is so far just a nice dream?
No, it's more than just a dream. No, there is already something. Actually, I could have put also the link to the GitHub repository we have. Look for github.com/cs3org. If I remember it right. I'll put it in the slides for afterwards. So what already exists, in fact, is the definition of the API. And okay, because these are new things, so this is all done with protobuf, the Google format to do remote procedure invocation, basically. And there is a kind of reference implementation that is the Sandbox daemon. So this Riva daemon, this logo that I showed, it is being rewritten using those APIs. So we are kind of proof concepting the entire thing on our own, like trying to integrate the different things as if we were to be able to talk to everybody else in the world or something. So respecting the API itself. This is just in the earnest part, let's say. But as the project is going to really start next year, the plan is to also have people coming at CERN, I mean, funded by the project, and then helping in the development. And I should add, okay, this is almost a commercial advertisement. OnCloud is very much involved, and they were very much interested. So on their own, they decided to endorse the entire thing to the point that the next version of OnCloud will be based on this. They will throw away whatever is there at the moment, their code base, etc., and they will propose a new version which is entirely based on this code that we are writing together.
Other questions? So you can ask any question to any speaker of that session now. Shoot at him. Nothing? Okay, then thank you again. Then we have at least 10 minutes more coffee break.
So yesterday at the museum, somebody lost a public transportation card, and it was found by the museum people, and somebody took it with them. If that somebody could come forward and give it to us, that would be nice. We know who lost it.
Okay, so now it's the last part of our storage and session, and we have a talk from Oliver all about CephFS and many different aspects of it. Over to you.
Thanks. So I think we can go with the short title, CephFS and more. So basically I will walk you through all these points which are condensed in the title. So first I start with where I'm coming from. You've already heard that in Peter's presentation on Tuesday. I come from the Physics Institute at the University of Bonn. We have 240 members, 1,500 registered network devices, which we are basically administering at least in part. So 160 managed desktops, some managed laptops, 50 managed servers offering local services, and compute nodes. And in addition, some hundreds of unmanaged Windows, macOS, and Linux systems, which the groups themselves are hopefully administering or letting run in some way. Then we have the biggest particle accelerator of a German university with 2 local experiments. And in total, we have not only groups from high energy physics, so mostly Atlas and Bell 2, but also hadron physics, which are working at this accelerator. Then detector development groups, photonics groups, and lots of theory groups doing development. For these, we need the HTC cluster, and we need to cover also all these service requirements. And these can be very diverse, as I will outline in the following slides. So here we use CephFS for in basically all the roles which CephFS can cover. We use it as a file system in our computing cluster, where we have at the moment a bit over 1,000 cores and half a petabyte of CephFS storage. We use erasure coding here. I will go a bit more into detail later, and compression on the fly. Then we use for our virtualization cluster as back-end Rados block devices, or short RBD. This is a small 9 hypervisor cluster with 40 VMs at the moment, which is still growing. We manage that with 4-man using QEMU KVM and libvirt. It's rather small and not really fully used because we don't use so much storage, it's just services which are running there. It's a 3 replica setup across 3 different buildings. And finally, what we are starting to use now is Rados Gateway, which is basically the S3 front end to Ceph. And we want to use it as a backup storage initially, potentially also for CERN VMFS and maybe other tasks in the future. And again, this will be a 3 replica setup across 3 buildings. So I start with CephFS. Here we had an old cluster with Lustre running for quite a while, over 10 years, with never updated Lustre and lots of problems, broken syscalls and stuff like that. Then for a successor cluster, we initially considered using a new file system with less maintenance effort, with InfiniBand. And we designed that when we wanted to order it for Lustre and BGFS, because that's basically what we knew, and BGFS would have had less maintenance effort than Lustre. Testing was successful of BGFS indeed. It was really well performing, but the free license didn't cover our needs. So we wanted ACLs and quotas for our users, and this would have meant you need to have a support contract. Also, we found that contributing to code is complex unless you have support. And that's not something we want from a project which we have in wide use. So we switched to plan B after buying the hardware to CephFS, beginning of 2018. So as you see here, if you go through this list, I will not go through it in full detail. The hardware was initially only 2 servers which take care of monitoring the system and metadata for CephFS. We added in black 1 more, because you should have an odd number. So they don't disagree on the things, on the cluster status. And then we have, at the moment, 7 OSD hosts. This number is growing, which have 32 HDDs with 4 terabytes, and we now will buy the first host with 12 terabyte disks soon. The main thing we did here, first, is to upgrade the memory. We had only 64 gigabytes. For Ceph, you want to have more for stable operation. And we also added NVMEs in this new host and soon also in the older hosts, which keeps the local metadata, so where the blocks are stored on the disks for CephFS. In addition, the metadata of the file system is stored on NVMEs and SSDs in these 3 small servers up here. So what's a bit special, if you know a bit about Ceph, we have the metadata stored on the same servers where the metadata servers are running, which means you have nice performance, but usually co-location can cause problems. If you have enough memory, it doesn't. So setup details, we are using erasure coding, which means that everything is cut into 4 pieces. There are 2 additional parity pieces, and then they are distributed across 6 different servers. On-the-fly compression, we are running CentOS 7.7 everywhere, and may also upgrade to CentOS 8 once Ceph packages are available. We export everything with NFS 4.2 to our desktop machines, so users can access the cluster storage from their desktop using NFS Ganesha. In the cluster, we use the Fuse client. I will come back to that a bit later, why we use the Fuse client and not the kernel client. The main reason initially is that we can do upgrades fast, but it also has some nice side effects for us. We also use quotas and ACLs, and not all these features are available yet in the current kernel versions, which you get with the LTS operating system. Then we use IP over InfiniBand. We had some issues trying with RDMA. You may be able to get it to work, but it's a bit complicated with Ceph still. And after tuning, IP over InfiniBand is working sufficiently well for us. We have grid connectivity with xbootd and WebDAV, 7 gigabits at the moment. This basically scales with the number of servers. And the main message I want to give to you, the mailing list of Ceph is very responsive. If you have any problem, contact them, and experienced people will answer. So we never missed any kind of commercial support. And also, we tried to break the system, of course, in the test phase, but we also did some things afterwards which you would not do to every file system. So we upgraded the RAM of all servers without downtime. We added 1 more server. We added this additional third metadata server. We changed the failure domain, which means where the data is distributed amongst the servers. So almost all the metadata was shuffled around. We exchanged HDDs, of course, if they break. We had a hard lockup of some disk servers when we still didn't have enough memory due to kernel bugs. Then we did some major upgrades. We will do the next one soon. And what we will do even earlier probably is reinstall 6 of our 7 disk servers and purge all the data and redistribute it when we add NVMEs. And you would probably not do that with any file system. At least now we are confident enough that it will be stable. Now I come back to the quotas. We have a kind of special setup. Every user gets 500 gigabytes plus unlimited grid storage, basically. But we also limit the file count. You can give a limit on the number of files with CephFS, and we have a limit of 100,000 files here, which prevents users from storing software there before they contact us. And it also prevents an overload if you create many files in a small time. This is also limited, as you see here, by using the CephFS client, of course, because metadata operations are then slower. But our use case is write once, read many, large files, which is the classical high-energy physics use case, so this is not a problem at all. We get nice sequential throughput, and it's not a problem if accessing small files is slow. Additionally, we use CERN VMFS for software. And I think in this community, I don't need to explain that it's a Fuse operating system with exported via HTTP. But I should also mention that we can use S3 as backend, so maybe we will also migrate that from our own server infrastructure at some point to a Ceph-backed system. So just a small plot. What is the throughput we get? This is the outgoing InfiniBand traffic of the 7 servers we have at the moment. And you see that when users really write efficient code, they can bring the system to 6 gigabytes per second from these 7 servers, which is mostly limited then by the disks even, and not by anything else, not by compression or stuff like that. You have to be a bit careful here because this outgoing transfer includes the overhead from the erasure coding, because this includes the servers talking to each other to reconstruct the objects from the erasure coded parts. So it's more or less like 4 to 5 gigabytes per second. It's not too much difference from reality. Now I come to the next point. We also use Ceph for virtualization as Vados block devices. In the past, we had a system based on Scientific Linux 6 with LVM on RAID 1, and you could really feel that the I/O was slow, especially when you did full backups every day. Now we have all systems on CentOS 7.7 running a recent Ceph release using libvirt with RBD backend. In addition, there's also a CephFS where we put the XML files of libvirt to have them synchronized across all the hypervisors. The machines are currently only connected with 1 gigabits Ethernet, but that's sufficient for our services use case, so we use a few % only of that. And we use write-back caching. This basically means if you run fstrim, then all the unused blocks will be trimmed in Ceph, and they won't use any space. This is the unmapped discard call, which is used in the back, and this is how it looks like if you configure it in libvirt. So you write here cache write-back, and you write discard unmap. Write-back caching means that also the writes are stored in memory of the local hypervisor and only flushed out to the backend after some time, or if you issue a flush syscall or issue sync. So this is still safe. This is what's happening also on your local machine, but it really gives you a lot of more performance for networked file systems. So this is working well for us. However, there are, of course, you might be anxious if you do something like that. So before we went into production, we did some funny things like having VMs writing stuff to the backend, pulling out power plugs for over 10 minutes to check if there's anything bad happening. And first we pulled the plugs of a single storage server, then of all storage servers, and also of the metadata, so the mon servers which watch the system, and we put them back. Ceph continued to write as long as it was possible, so if you have still sufficient OSDs available, it continues to write. Afterwards, it blocked writing, and once the servers came back, it continued. No downtime of the VM, no hanging VM. Of course, while it couldn't write, it was stopped, but it continued where it left off. If you, of course, also pull the plug of the hypervisor, which would be a problem if this write-back caching would not work as expected, then you could break the file system. But indeed, we didn't observe this. You only have to run E2 FSTK, which the system does automatically when rebooting, as you do on your laptop when you have a broken battery, for example. There are some important gotchas here, and you want to try this at home. Unmapped discard is only supported with virt.io SCSI and not with the virt.io block driver. It was added in 2019 actually to virt.io block, but probably you won't run this in production yet. You can check these kernel commits and QEMU commits if you have that patch in. And virt.io SCSI usually has another problem. If there is 30 seconds of disconnect to the emulated SCSI device, then normally an actual hardware machine terminates the SCSI connection because something is wrong. With networked stuff, for example, when we pull all the plugs, this would be bad because then the VM would not recover. This has been fixed in 2017 for this special use case. in the kernel, and Red Hat has backported that to Red Hat 7. So with CentOS 7, you are on the safe side, and if you use something else, you can check the kernel commit if this is applied to you. The hardware is not too heavily sized, so you see these are 3 small servers. You could actually also co-locate that with the others if you want to go even cheaper. Then 3 OSDs with 32 gigabytes of memory and 3 OSDs with more memory, and all have 4 terabytes of HDDs, and these are then distributed across 3 different buildings. At the moment 3 different rooms, but once we have a building more, then it will be 3 buildings. So we have 3 replicas, and any building can vanish for a short time if the cooling system, for example, fails, and things will continue to run. We can even put in more HDDs, but at the moment the usage is very small. And Ceph takes care to put the copies in the different data centers, which are just 3 rooms. The important part here is the backup. In the past, as I mentioned, we did full backups with DD of the full disks. Now we can do some things more cleverly. So we have now a backup with dailies, weeklies, a few monthlies, and could also keep yearlies at the moment. And we can even tune the retention as we want. The nice thing here is that we only do incremental backups. So what we do is first we tell the VM to trim the file systems. As I told you before, we have activated that for all the RBD volumes. So this means any unused space is also freed up in Ceph. Then we use QEmuGuest agent to freeze the file systems. This runs the fsfreeze commands in the VM. Then all the file systems are frozen and all the dirty buffers are flushed to disk. So if you have a database, this should be a consistent state, unless the database does something wrong. Then we take a snapshot of all the block devices outside, so using Ceph commands. And then we run thaw again to thaw the file systems, and the system continues. If there's not much I/O going on, this doesn't really cause load, and this maybe frees the VM for a second or so. If there's heavy I/O going on, then of course you may need a different solution, but for us this works perfectly fine. Then there's a second phase running on a different server, so the VMs don't notice anything of that. We are at the moment using Becky2 and Benji backup. We will in the future use only Benji backup, because Becky2 is in some ways a predecessor. I will go a bit into more detail later. These tools allow you to back up Rados block devices efficiently. So I will go into more details, but they take care of backupping all the changed blocks only. After this has run, we will remove old backups. We scrub the backups also with these tools. And we remove all snapshots actually from Ceph to free more space. So what is Benji? What is Becky2? Benji is basically a more active fork. We use several of the features, for example, the incremental backup. This uses RBD diff to get the changed blocks directly from Ceph. Then it backs up the chunks at the chunk size, including checksums for all the chunks. It uses strong compression with Z standard. We have it set to the highest level because this really saves a lot of space. We scrub the backups with this tool, so we know we can still restore them. And you can even mount the backups with NBD if you just want to fetch one file from your backup from a few months ago. What we are not yet using is encrypting the backups, but this is also supported. Then at the moment we back up to a machine with ext4 and a simple RAID 6, so nothing special. But in addition, we also keep the snapshots for a while. So we have in the end 2 places where data is stored. As I didn't mention yet, the backups only take a few seconds because it gets the list of changed blocks, and this is usually small, some minutes if you, for example, installed a lot of updates. Restores to Ceph or also to raw image files. If your whole system breaks down, you can just recreate an image file and run it in QEmu. This works very well, so we tested that. And what we are doing right now is commissioning RBD mirroring. So we basically send a live stream from our virtualization cluster to another Ceph cluster with all the changes. And then you could also restore from there, including the snapshots. So some interesting observations about this backup technique. If you have low I/O, the backup time basically scales, or the number of chunks which are backup, which is directly the backup time, scales with the size of the volume. So if not much changes, there's always seems to be a minimum amount which is backed up. And my explanation for that is that this is probably just the superblocks of X4 which are changed every day. The backups are very well compressible, so you get ratios between 10 and 100, because if only the timestamp in the superblocks is changed, there is not so much. So we used set standard level 22, and it is really fast. It takes a few seconds to minutes. So the space usage for 40 VMs with full software installation, so it's CentOS and the full service is running there. We keep 4 monthlies, 8 weeklies, 14 dailies at the moment, and this is 1 terabyte for 40 VMs, so it's basically nothing. With Becky, it's a lot, so this is just the snapshots. With Becky, it's more actually, because this keeps a bit more history, 1 month more. With Benji now, with the compression, we get for even 8 monthlies, so more than this, only a quarter of a terabyte. So the compression really helps. So the conclusion is the backups are small, probably just superblock copies. The compression helps significantly, even if you trim, because that's the main space saving here, of course. We don't use the full volumes. And for servers with low I/O turnaround, as you saw, you can keep even a year of monthlies without problems if you find a bug 2 months later or don't understand why a system ever worked, which sometimes happens. You can check in your old backup. So finally, we also are using S3 or starting to use it. So we now start to commission a Ceph-based backup system. So we have a new system using Ceph Nautilus, which is the very latest release. And actually, we installed it 2 weeks ago, 3 weeks ago by now even. But I only had 1 week to investigate it. And I'm very delighted by the new dashboard. I will show you a screenshot in the next slide. And automatic placement group scaling. If you have ever done anything with Ceph, there's one magic thing which you need to do, which is to guess the number of placement groups you need, which is in the end a guess of how much data you store and how large your cluster will be. And with the latest release, you don't need to guess anymore. You can change it afterwards if the guess was wrong. And you can even do it fully automatic. This backup system we want to use as storage via Vados Gateway, which allows you to do backups with Restic on Linux, for example, or with Duplicati from any operating system, basically. This is a nice tool which also does deduplication, incremental backups, and you can encrypt it locally. So if you have users in your institute which want to back up, they can store it there safely without even giving you the key to the data. We did some first tests with a single Mon server, a single OSD server, and a single Vados Gateway machine. And we got already with this 10-year-old hardware which we used there, 50 megabytes per second from a Windows machine. So this worked rather well. And now we want to scale that up basically and distribute it across 3 different buildings. We are still discussing whether we need other interfaces, maybe even a CephFS, if we want to use Time Machine on macOS, or if we want to offer XBooT for experiments. But maybe even with S3 we could be happy. So we will only do that if users really request it and have a useful explanation. Also, this cluster is already mirroring all the virtualization. So all the virtual machines you saw before. And this is basically a live stream of data of 1 megabyte per second. So you see there is not much going on in the virtualization cluster if you only transfer the changes. And this is done asynchronously. The next release of Ceph, coming out next year, will even have a new feature to mirror only the snapshots and not the actual live stream. So we could even throttle that to basically just a few megabytes per day overnight, if this ever becomes a problem. Also, I should mention that if you do mirroring, at the moment you need to enable journaling on your Vados block devices, which almost costs a factor of 2 in I/O performance at the source cluster, so at the virtualization cluster. With write-back caching, this goes down to a negligible factor. But in principle, if you don't do write-back caching and if you have high I/O loads, this could be a problem. So in the next release, when you only mirror the snapshots, you might gain a lot. For us, it's not too important, but maybe for others. So as I promised, here's a screenshot from the Ceph dashboard. So it's a web page you can visit. It's directly built into Ceph. You can, for example, here see all your OSDs, which are in this case just 9 disks in a small server. You can even push buttons. You can say, I want to scrub this disk, check if everything is still okay. I want to mark it out or down. Maybe you want to remove it at some point. I want to purge this disk, so Ceph really forgets about it. And then you can, yeah, if you know a disk is soon failing, plug it out. And yeah, Ceph Nautilus also has some nice features like detecting beforehand if a disk is going to fail with machine learning. So at some point, it's becoming more and more automatic. So I put one extra slide after the last Ceph day. Why do we look at S3 and Vados Gateway? So one case for us, of course, is backups. But the nice thing is that it might also be useful for other cases. So you could also think about storing data from experiments there. Basically, S3 is an HTTP or ideally HTTPS protocol with a lot of existing tooling. You could even host web pages on it. But it also has some features which are not too heavily used yet, I think, in our community. This is site-to-site replication and also tiering. You can put caching layers in front. And you can also even shuffle data if you want to Amazon and store it as backup there. If you prefer, you can also encrypt it, of course, in this case. It already has token-based authentication. You could even create users in there and replicate them to a different cluster. So you could do federated storage. It has lifecycle policies, either to migrate data to more cold storage or to delete it, if this is possible for your data. And it offers redirection. So what you also need for federation, of course, is if you don't store exactly the same data, to redirect to the place where the data is stored. And what's really interesting, what was now added to the roadmap for the next and the release after that, what Ceph Vados Gateway wants to add, the site-to-site replication and also data migration will now be possible per bucket. So basically, you can emulate third-party copy, which we are now doing in the grid, by just telling the bucket, copy it to another place or to two different places and keep it in sync. What's really new and what you can think of a bit as like Xcache is transparent live migration of data while you are reading and writing. So say you start a job at a different site, you can live migrate the data while you are already reading it, and then it's local at some point, and at the same time you can already read it and write to the same bucket. And you can also pass through external storages, which could be public cloud, but could of course also be your local tier 1 center with a lot of storage. So this could be interesting for smaller experiments starting with DDM. It will probably not replace FTS or Rusio anytime soon, but it's something you should keep looking at. So in any case, you can also have encryption, tiering. All the features will be possible even with this model. So finally, I conclude. CephFS can also work well for HTC clusters. So what's important to keep in mind, you should have a separate FS for software. And you can also use HTCondor file transfer for software. So keep in mind, as you heard also on Tuesday, don't put many small files on CephFS. As with any cluster file system, this is slow and inefficient. Then you can use write-back caching and trim discard with Vados block devices. This is not yet too heavily used, but it works very well, especially if you want to back up everything. The backup with Benji is working very fast, as you saw, and you can really store long histories. And you can mirror everything to a different cluster. We are now taking the first successful steps with Vados Gateway as a backup service. And you should keep an eye on this functionality because now Red Hat is also pushing it. So maybe this will become really, as promised, a full-fledged site-to-site federation service. And if you want to start with Ceph, or even if you're using Ceph and wondering about some things, don't forget there's a very active mailing list. Experienced people answer, sometimes even within 10 minutes, as a support guy who takes thousands of dollars would. And they even tell you what is wrong and not only how to fix it. So with this I conclude. If you have any questions.
Thank you very much. Any questions for Oliver? No? Okay, then we'll thank him once again and move on to the next talk. Yes. Which one is it? Is it the... Okay, so now we'll hear about...
No,
oops.
no, that's not... maybe the next, the previous one, maybe.
I'm sorry. It's this one, yeah.
Sorry, it didn't show the number.
I'm very sorry. Right, okay, now we'll still hear about storage statistics through Hadoop.
Ecosystem, yes. Hello, I'm Antoine Dubois. I work at the IN2P3, obviously. And I would like first to thank my colleague, Hosman, who helps me to write this presentation and with whom I work on that project. So, first of all, I will do a bit of context, then explaining the project and draw some conclusion. So, as you may all have in your data centers and services, well, you have lots of storage system, lots of storage element organized in different ways. At IN2P3, we have decided at a point to expose, well, iRods, Dcache, IGPSS, IXUD, won't talk about them. Just to explain, SPS is our high-performance storage for HTC, mainly. And PBS is a service that is exposed to user, and it's mainly backed up permanent file storage. So there is the home folder of users in here, and there is also the software sharing and the web application we host. So data that we need to keep and to back up. Some figures about all the storage system. The most important one I want to focus on is the number of total files at the moment, so around 1.7 billion files. And if you want to describe those files, as in a file system with the dates, the access date, modified dates, and size, and things like that, at the moment, it's around 400 gigabytes of raw data. So it's already a lot. But you all know that science won't stop here, and that we are expecting the LHC Run 4 in the years to come, and that they promise us to generate more data than ever before. We also have LSST, because we are one of the replication sites in Europe, and the catalog for data only should be around 15 petabytes without any experimental computation, just a catalog. And we also host Euclid data, and well, they expect at least 10 petabytes of usage in the next 5 years. And with all that, we estimated that all the metadata of our storage element could rise to up to 4 terabytes in 2030, which start to be a huge amount of data. So what is this project? First of all, why we need it and what we need. Because at the moment, we obviously already have statistics about our storage, like everyone here. But at the moment, every storage manager does his own statistics, sometimes because someone asks him a lot, because sometimes he needs it. And everybody does what he can, but we want something centralized. That's really important. As I show you, we want it to be scalable, because we will compute statistics on a regular basis, and 4 terabytes of regular data to process, we need at a point to have scalability. And one of our objectives at the moment is to be able to compute any simple stat, such as the file size of a user, with the same code on any file system at a given point in time. We also want to be able to compute specific storage stat for a specific file system. So, for example, does the file are hosted on disk or on tape for Dcache? That's only an example. And the most important thing for us is that we need those data to be available for people inside the CCN 2P3 so they can either consult the statistics we are going to issue or to consult the metadata themselves so they can run their own statistics if they need some. So if they want to develop a new stat because they feel there is something missing, they could just try it out, execute some code, and when they find the proper statistics, they could ask us to compute it regularly. So we also need it to be regular. So that is a bit ambitious at the moment. So let's fix some first goals. We want to reproduce what we already does on this new system. So we will try to reproduce what the storage expert already does on their storage on this new solution. We want quickly to enable an access to all the metadata describing all the files through all the storage elements. And we want to give an access to the management team so they can use Tableau most likely to do visualization for decision making. So how do we think about doing that? First of all, we start by extracting the data. So we asked all the storage manager for each services to export those data as CSV. So they can do it the way they want. They have the choice, and we ask them to put the maximum data they need to do their own stats. So for HPSS, you will see there are specifications, and for each file system, in fact. We use a small tool I developed in Scala to transform those data into a Parquet file, which will have the same column for all file systems. So we can issue the same request on any file system. And from those Parquet files, we will give an SQL interface using Hive. So anyone can just consult those data using Hive, because SQL is a fine language and quite well known at this point. And we will use Spark as well to compute the regular statistic we need on a regular basis. And at the moment, we send them to a Postgres database, but I have tested it on JSON for storage on S3 or on MongoDB, Elasticsearch. Well, anything works at the moment. But in fact, if you want to have something, a global visualization of all file system, that's a bit of the explanation of well, all the file system. That is the most common column we can find on all our file system. But as you can see, for iRods, for example, we don't really have a UID or a GID. So we maintain a separate table to have some correspondence with our actual UID and GID used on the batch. But we have their username and group name, as you can see. So we could guess those values. We won't have those. And, well, you can see. Also, I don't know if you have users in your data centers or using your storage space, but I don't know if you know how creative they are when it comes to file names and what they can put inside it, like invisible Unicode character that no one knows about. That's quite amazing. They are quite creative. So we will take all those columns with specific value and common value and transform them to this Parquet file with basically a service name. And what is the most important here is, well, first we do some treatment to detect the extension of files and characterize them. So we will have a video when we detect an MP4 and .avi, things like that, and the experiment file like root file or Python file. We will improve this as it goes. And we have 5 optional columns for each file system. Some are empty, but I think now we are the most used is 4 columns for one file system. But We said we took 5. Maybe it won't be used, but 5 is enough for now. So the system is running at the moment on a small virtual machine cluster with 4 nodes, 8 CPUs, 30 gigabytes of RAM per node. That's a bit too much RAM, but it works. We are not using HDFS to store the data. At the moment, we are using CephFS, shared between all the nodes. We did that because we have tried S3 and HDFS, and in fact, we didn't want to add a new file system to the file systems. So we have a Ceph instance at CC, and we ask for CephFS shared storage. And at the moment, our only issue is that our VM have 1 gigabyte link, and that is our main constraint for the moment. The Hive part is still in testing. So, as of today, the data for what we call PBS, so our backed-up storage, are compute since 1st of July on a daily basis. For Dcache, the data have been integrated mid-September on a weekly basis because we considered that Dcache wasn't such a moving file system. Maybe daily computing wasn't really relevant. And well, I think that in the months to come, I think end of November, every data will be integrated and processed. But what we can do with that? Well, for example, those two graphs have been made with the same request on Dcache and on PBS. So here you can see the type of file stored in number of file. So we see that Dcache mainly have root file, which seems quite normal as it's a science storage space. And on the home folder of users, we see that, well, we have lots of unknown file, dotted file, which are hidden files. So obviously in your profile, you have lots of hidden file on the base. And well, our users do a lot of code because because this is a Python and this is the C++. So our users are coders apparently. We could also compute specific statistics. For example, here this is the difference between the visible size of file and the used block size of our file. And for the home users, the home folders, we have lots of small file, and we see that there is a huge overhead. So the visible size is 3.5 terabyte, while the actual disk on space on disk is 6.1, because well, block and disk mainly, you know how it works. Well, we could also start. We could also find out what is the most popular language at the CCA in 2P3. And apparently, at the moment, it's Python, because, well, I'm just sad that it's not Java. I love Java. Yeah, but yeah. HTC love Python. So this project at the moment is only starting. It's been a year. We have been experimenting a lot. We are in a pre-production run at the moment. But first of all, we need to integrate all the storage elements because, well, it will be useful, of course. We need, with the team and, well, everyone that needs statistics from storage at the CC to define a set of regular stats to have and to store and to make available to users so they can display it or use them in their presentation. We need to finish, and we are not sure how we are going to do that yet, but we need to find how to set up Hive properly. And as file names could be considered private data by GDPR at a point, we absolutely and definitely need to do some Kerberos integration so we can restrain access to this because we don't want it to be public and only people that are allowed to consult those should be allowed to do this. But that is only a first step because when you have all the files of your file system described in a database, what you can do with it is, well, only limited by what you can imagine. So, for example, we could add more file system because at the moment that is only the storage element that are exposed to users, but we could add maybe our Ceph storage, which is today used mainly by OpenStack instance. But we could also add TSM maybe, or databases. So lots of data to compute on the storage world. We also seriously think about using those metadata to validate data management plan. So we are defining that data management plans currently. And once assigned with, once defined it with the experiment, we hope that we will be able, for example, to give a report, like if we decided that no file should be 6 years old or more, a monthly report that says, okay, you have those files that are more than 6 years old. I don't know exactly how it will happen, but I think this should, that would be used for that. And also, well, a side project to analyze I/O and file access of jobs. I have done that for Euclid, and well, the script I made for them give me quite a lot of logs for one pipeline, probably around 100, 200 gigabytes of file access logs. So it takes time to compute, and there is quite interesting things to do with that, and I'm sure I will look this more thoroughly in the future. And with that, thank you for listening to me.
Thank you very much. Any questions for Anton? No? Okay. Well, thank the speaker again. Thank you very much.
Iris.
Next speaker is Iris,
Yeah.
and it's just I hadn't got sound. Integration and optimization of BNL storage management.
Thank you. Hi everyone, I'm Iris from Brookhaven National Lab, and today my presentation is the integration and optimization of the storage management in scientific computing data center, scientific data computing center in Brookhaven. I'm doing the presentation on behalf of the storage team in SDCC. Okay. This is the outline of my presentation. I will talk about integration and optimization from three perspectives. Start with data storage. In the storage team in SDCC, we use we store the physical data in Dcache and X3D, the data from the experiment in Dcache and X3D. We allow the users to use BNL box to store a small amount and small size of the data, or they can share the data in the BNL box. Dcache, X3D, and the BNL box all talk to the tape system. We use HEPiX in SDCC. Another perspective is the data transfer. I will talk about the protocols we are supporting and the protocols currently we are testing. And you heard a lot about the data carousel. Yeah, this is what it's I would say a little bit painful for me every time is because the production is going on, and this has a very intensive staging retest also going on. So we have to make sure that both works very fine. So I'll talk about some experience and some optimization we did to achieve the best performance in the data carousel at BNL. Okay, another thing is the last one is the data access pattern. This morning you heard the PEP about the data access pattern for CMS data. It's very interesting that we recently did the same thing for the Atlas data. So I'll show with you the statics, some plots, and some future plan of this data access pattern study. Okay, let's start with the data storage. We have about 6 Dcache instances in Brookhaven. Here I list the largest 3 ones. That is Atlas Dcache, Beta 2 Dcache, and PHENIX Dcache. We are the tier 1 site for Atlas and Beta 2. We are the tier 0 site for PHENIX Dcache. These 3 Dcache add up about, the disk space add up more than 50 petabytes. For the STAR experiment, we store their data at use X through D. Because JBOD is relatively inexpensive and relatively easier to maintain and scale up, so we use JBOD a lot in our storage. Like Atlas and Beta 2 Dcache, they are purely on JBOD for the storage. For PHENIX and PHENIX Dcache and STAR X through D, we store the data on farm node before. Starting from this year, we bought 3 petabytes for each instance, and we are slowly to move the data from the farm node to the storage, central storage with JBOD. Why we want to do that? Because the farm node it's not a dedicated storage system. They have to share with the jobs. And then another thing is that the farm node, they are not stable, especially for those very old ones. So it's quite often that they will lose the connection from network, or sometimes they will just crash. So we have to inform the user that your data is not there. So we have to stage it from tape if they have a copy there, or stage from or copy from somewhere else. Another thing is that the performance, the throughput of the farm node is not as good as the central storage. So and even the farm node is shared that small amount throughput with other jobs. So sometimes it will take a very long time to retrieve a file from those farm nodes. So we decided to move most of the data to the central storage. So what we did is that, but because now it's like part of them is still on the PHENIX farm node. So we have to do a study of what kind of data we should move to the central storage. So we did a study of what are the hot data and what are the cold data. The data that is not accessed that often, we will keep them still on the farm node. This is already done transparently. So our next step for this one is to do an intensive staging test to retrieve data from tape to see how to configure the central storage in the system as the best effort and the performance result. Another thing that we are planning for the storage is for Atlas and Beta 2 Dcache. For the disk data on Atlas and the Beta 2, they have 2 copies. They have a primary copy and they have a secondary copy. The primary copy is in a slightly better host because they will not only be the primary data, but also serve the transfer as the first choice. They have the priority to serve the transfer. For the secondary copy, that they will only be used when that the primary copy get lost or the primary host, they are too busy. So now we are thinking that maybe we can use some retired disk and use the Ceph technology This is something in the plan that will be used as the secondary copy host. Okay, I'll move to the data transfer. Basically, our Dcache support all the long grid and the grid protocols. This year, we joined the DOMA to test the third-party transfer. That is to move bulk data directly between the endpoints. There are two potential third-party transfer protocols for WRCG. One is through X through D. The other is HTTP WebDAV, through the HTTP WebDAV. We test this third-party transfer in our Atlas Dcache. The Atlas Dcache, the storage pools is behind the firewall, but the doors is outside being a firewall. But when the storage pool behind the firewall, it gives some problems, gives some headache that if you want to use the third-party transfer to move the data directly to the storage pool. So what we did that is we attached some SSD in the door and then to use it as a hopping pool. So when the files from the client, they're trying to reach BNL, they will first go to the hopping pool. Then from there, they will hop to the storage pools behind the firewall. The HTTP third-party transfer is already tested through. So now we have a daily HTTP third-party transfer smoke test going on. We are currently, at this time, we're doing the third-party transfer for X through D. That we're working closely with the developer, that the hopping pool is set up on the door, now has a new XRDCP client that is almost finished. Okay, data carousel. I believe BNL attend every data carousel or every since last year, middle of last year. Every time we're trying to challenge ourselves, we not only found the problem, fix the problem, we're also trying to challenge ourselves. Like you can see that we start with the staging request that is less than 20,000. Then we increase it to the 20,000. Then in the middle of, in June, we increased to 60,000. In the latest one, the latest data carousel that is in August, the staging request assigned to BNL that increased to 100,000. So I found that, the latest one is a little bit ambitious this time. That is, we have some problems that we didn't see before. So when the request goes to BNL, it first goes to Dcache. Then Dcache will distribute all the requests to all the staging pools. We use the Oak Ridge batch system to pass the request from Dcache to the HPSS. Once HPSS gets the file ready, it will use HPSS PFTP, return back to Dcache. So in the presentation today, I'll talk about optimization and the problem we found in Dcache, in Oak Ridge batch system, and in HPSS, the three steps. Okay, in Dcache, after first round of data carousel, we found a problem that the first problem we have is that the staging pool, the size is too small. So what's the problem for small staging pools? If the pool is too small, before the client to read the file already get purged out. So that means the file has to be staged again from tape. This is a waste of time and a waste of resources. So what we did is that data we increased the size of staging pool. Now it's about 2.8 petabyte. This is good for most cases. Only in occasions that it will take very long for the file to get retrieved, that will lose a little bit data from pool. Then it will get again from the tape. This is easy to fix, just add more pools. But another thing that is not easy to do is to decrease the load of the staging pools. Make the pool stable, not crash, becomes so critical because every time we increased, the assignment to being increased in every data carousel. So now, the latest one in August, that we experience a lot of pools get crashed, and then they lost the data on the host. They also lost the staging request assigned to the pool. But we tried a lot to make the pool stabilized, and in BNL we used a pony mechanism to assign the staging request and check the status of this request. Here, at least that for the pooling rate, you can set it as 2 minutes, 5 minutes, or 10 minutes. That means that at normal time, the staging request, they are in sleeping status. They will not cause any node of the pool. After 2 minutes or 5 minutes or 10 minutes, they will wake up to check the status. At this time, it will cause node for the pool. If we have too many requests to wake up at the same time, it will make the CPU too high and just crashes. So we did a comparison of to achieve the best pooling rate. The 2 minutes, you see is a little bit high, the CPU. In 10 minutes is good, but in the carousel, if you after every 10 minutes you're going to check the status, it will just take too long. So eventually we put the pooling rate at 5 minutes. It's good for most cases, but now we are talking with the Dcache developers. We're trying to find a good way to achieve to make the pool as stable as they can. Okay, another part for the optimization we did in the carousel is in Oak Ridge batch system. HEPiX gets all the requests through the batch system. Our HEPiX is staging the request in a way that once they get all the requests, they will do a sort. Then they will go for the most popular tape to get files. So that means the bulk submission is the most efficient way to submit the request. Although data carousel is already allowed the bulk submissions through FTS, but when the rich decache, they still take a few hours. So all the requests come here, not at the same time, not concurrently. They will have a few hours to finish all the submission of the request. So what we did is that we want to hold the request in the Oak Ridge batch system here until it's reached a certain amount. We'll pass to HEPiX at one shot. So this is something we found that it will improve our performance in the data carousel in the latest data carousel in August. Another thing that if has too many, but we found that we cannot make this number as much as possible. It do have a limitation here too, because the Oak batch system just failed the work. It's just hanging there if the request is too much. So we still need to find the best number to feed the batch system and feed HEPiX. In the HEPiX, they also has a disk cache. Currently, our HEPiX can hold 6 hours. So the data will be here for 6 hours. After 6 hours, if the cache still does not retrieve it, it just simply be purged. But the cache is not smart enough. If they found that the file is not here, it will not retry immediately. It will go to HEPiX directly. So this is what we don't want, because HEPiX want bulk submission. They want all the requests from a batch system. So we'll add a check every time when HEPiX is trying to retrieve file from disk cache to make sure that the file is still there. If it's not there, then don't go to HEPiX directly. Another thing that we used in the latest data carousel because HEPiX PFTP client is used to transfer the file from HEPiX to Dcache. that we add a few of them this time to make it as a round robin. Monitor in data carousel is very, very important, that we want to make sure that every step is monitored. So here is monitors from monitor the HEPiX. This plot is monitored number in the batch system. How many numbers were in batch system? How many of them submitted to HEPiX? How many of them returned back to Dcache? How many of them failed? This is a very helpful plot. Then within the Grafana, we add another plot. This is for the transfer rate to see the size of files in and out of HEPiX. Monitor staging in Dcache. This is a little bit tricky. That's why we finished this all this plot recently, because Dcache log when the log the staging is they will only log it when it's finished, and when it's finished, it will not log when it's finished. It will log when it starts. So it's not easy to monitor the staging request in Dcache. That's why it took us a while to finish all the plots slowly by slowly in every data carousel. This is the number and the size, and here has a histogram and the heat map files. That is very useful to see. We can see the overall performance of the staging request, like this one. This is the how many number of files, staging files. How long does it take? So we want the first bar is as tall as possible. That means is the whole overall performance is good. If a lot of requests goes longer in this way, that means we need to check that the system to have some problem there. Okay, I finished the data carousel. That I'll move to the last part of my talk. That is a part of the study in an R&D project. Is data access pattern. This is what we did recently. We're trying to understand how the data in Dcache that be used and be. We studied in two ways. That is for the files that never accessed in certain time. It can be 1 month, 2 months, 3 months, or half year, or the whole year. Another is the data population. That is for the files that were accessed, but how often they were accessed. They may be accessed once, or more than 10 times, or more than 100 times in certain period. So unfortunately, Dcache does not, because Dcache has 3 databases. They have a camera database that has all the namespace information of all the files in Dcache, and has a binning database, that is the transaction information is in binning database. And SRM database holds the information for space token. Unfortunately, none of the single database hold every information we want, all the information we want. That's why we have to combine all the information from the 3 databases then to generate what the statics and the plot. It's really take a long time. This is something that is we want to improve. Okay, this is the population plot. Has in different time intervals. The one here, the blue one here, is for the data population for data disk file. This is only for data disk file in Atlas Dcache from June to September. That's the 3 months. The x-axis is about number of time is read, is accessed. And the y-axis is this is the number. So this is the number of files, and this is the number of reads. At first, when we first generate this plot, we don't know whether we should put as 1, 2, 3, 4. That means read once, read twice. I start with 10 here, 10, 20, 30. Then I found that actually for Atlas Dcache, For disk data, this is the best intervals to describe their arrays. And then I do we can easily change the time intervals. This is for the reading in August. If you are interested in the number of arrays above 10 times, we can go further here to see. So far we found that the highest one we found is that the files read more than 100 times. That is his files, some his files. So we try to understand why and the reason behind that. Okay, this is for the unpopular files. That means the file is not accessed. We only listed for the last 6 months. This plot is for the volume. The volume, this embeds, volume embeds. This is the not accessed in 1 month, not accessed in 2 months until 6 months. And this plot is for the number of files. This is size, this number of files that is not accessed. We're interested more on so far for the file that is not accessed. So we go further to see the type. The type here is basically by the file name. If they have the certain the character we are interested, we categorize them as one type. So you can see that DLD and LD, there are 2 types of files that occupy the most of the space that is not to be accessed. But then we found that if you look at the number, the log files, that is, the number of log files still has, is the majority of files that are not accessed. Fortunately, log files, they are small. So that's why the size of the log files is only a little bit. That is not accessed. So has this data in mind? This is some future work that we want to work on. First is that at this time, we will only concentrate on certain type, that is AOD or DAOD. We will only concentrate on those simulation types. And also another interesting question that we want to understand that if the file is not accessed in 1 month, will it be accessed in the 2nd month? Or will it be accessed in the 3rd month? So this is something that we want to look at. Another is the performance, to improve the performance of the, to get data from the database, because really the Dcache database is taking a very long time to generate the plot we want. Currently, this access pattern study is used for the Bing Air Lake project and also some machine learning project. So we'll see how it goes, and hopefully we'll soon find the information of this. So that's end my presentation. If you have any questions, come to ask. Thank you. You did? Oh, okay.
Yeah, you said optimization for the tape carousel. So on what levels? So on what levels did you do the optimization? So one was sort of the size of the staging pool, you said. I mean,
size of staging pool.
And what others?
In here.
Okay.
In here.
Okay.
Yeah, I mean, Let me see. Before the first data carousel, because the staging pool is not that critical, all the files they are not precious files. So if they be purged out, we just stage it again from the tape. But in the data carousel, there's so many files get purged out and so many requests come in. So we want to keep the file on the pool at a certain amount,
So
at 48 hours.
the pool doesn't have the size, at least the size of the recalled data. If you recall 1 petabyte, you should have at least a pool of 1 petabyte, right?
You mean for the data carousel?
Yes.
No, not in the beginning. Not in the beginning. I mean later they say that you should have the buffer at that size. But when we just start, we don't.
You don't know the data size that's going to be recalled in advance.
Yeah, in the very beginning. So that's why we had this problem that when the FTS, the routes are trying to gather back the file, we found the file is already gone. So then later, this come out this requirement that each site has to prepare enough of space as a buffer. Okay. This is my understanding. Yeah.
Did you change any other tape settings or?
The tape setting. For the tape, that every time, really in the data carousel, we do have to make sure that enough drives were assigned for the data carousel. So at the meantime, if we also has a lot of production going on, that will be a little bit awkward. Yeah, but this is something. I mean, this is something that we have to. Yeah.
Okay. Thanks. Yeah.
Okay. Thank you.
Okay. Any more questions? No? Okay, well, thank Iris very much again. Thanks very much. Okay, no further announcements, so I think we're done for today. See you tomorrow.
service.